So in this video, we're going to take another look at another optimization problem. So in this problem, we're going to construct a glass window with a fixed perimeter. So let's say that we have a fixed perimeter of 100, and we want to construct a window that has the maximum possible area. So we want to maximize the resulting area of this window. Now this window is going to be the shape of a rectangle with a semicircle on top of it. So first of all, to approach this, we need to define our variables. So since the rectangle has two arbitrary dimensions, we can define those variables x and y. Now that we have our variables, so given the exact values of x and y, we have a specific window because the size of this semicircle is dictated by the length x of the rectangular window portion. So, or the rectangular portion of the window. So next we want to look at our the perimeter and the area and express both of those as a function of x and y. Now we'll use the perimeter as a constraint equation. So we'll use the perimeter equation to eliminate one of the variables. And then we'll use the area equation to actually optimize. So we'll do calculus on the area equation. So let's start with the perimeter. So the perimeter, let's call the perimeter P. So let's define this as the perimeter of the window. So P is going to equal, well, we have length x at the bottom, so it's going to be x plus, we have a length y here, length y there, so x plus 2y, and then plus the perimeter of the top. Now the radius of the top is going to be x over 2. And the circumference of a circle is 2 pi r, so the circumference of half of a circle is just pi r. So this is going to equal pi x over 2. So basically our perimeter equation is 1 plus pi over 2 x plus 2y is equal to 100. So that is our constraint equation. Now the area equation is going to be, well, the area of the rectangle is x times y, and then plus the area of this semicircle, which is going to be 1/2 of pi r squared. So pi r squared will be x squared over 4, so it's going to be plus pi x squared over 8. Because for the full circle, we would get area pi r squared, which would be pi x squared over 4, then we have to divide that by 2. So from the perimeter equation, which gives us our constraint, x and y kind of appear equally. It's no more difficult to solve for x than it is for y. Now in our area equation, y only shows up once, so let's solve the perimeter equation for y. So we have y as a function of x, and then it makes substituting into the area equation a little bit simpler. So from the constraint equation, y is going to equal 550 minus, now 1 plus pi over 2 is the same as 2 plus pi over 2. And when I divide that by 2, it's going to be minus 2 plus pi over 4. So in order to satisfy the constraint that the total perimeter is equal to 100, the length y has to equal 50 minus 2 plus pi over 4x. Forgot the x there, but there's an x right there. Okay, so 50 minus 2 plus pi over 4x. So the resulting area, so now basically x is the only variable, that can be chosen. And before we proceed, what are the boundary points? So the extreme point, obviously if x is equal to 0, we get something with 0 length and it has it's just a vertical line. So x is going to be between 0. Now what's the other extreme? If x is long and y is 0. So if x is like that, and then we have the semicircle will basically, well, if y is 0, we just get a semicircle, right? So if y is 0, so basically this is just x like that, and then this length is x over 2, so the perimeter, well, okay, so y is 0 here, so x would be 200 over 2 plus pi. And if you plug in 200 over 2 plus pi for x, you should get y is equal to 0. Okay, so that's just a quick sketch of the domain for the x. So next we want to, in our area equation, replace y with this function. So it's going to be x times all of this. So that's 50x minus 2 plus pi over 4 x squared, and then plus this. So plus pi x squared over 8. Now we can combine these two terms. So common denominator would be 8. So that's equal to 50x minus 4 plus 3 pi over 8 x squared. So it's going to look like that. Right, so I multiplied this one by 2 over 2, so I get 4 plus 2 pi over 8. 2 pi over 8 plus 1 pi over 8 is 3 pi over 8, so there's the common denominator. So that's the area equation, so that the constraint's satisfied. Okay, so now to find the maximum area, we just take the derivative, set it equal to 0. So dA dx is going to be 50 minus, the 2 comes down, so 4 plus 3 pi x over 4. So the 2 came down and 2 over 8 was 1 over 4. And we set that equal to 0. So basically 50 is equal to this, so we cross multiply. So x is going to equal 4 times 50 is 200 over 4 plus 3 pi. Now 4 plus 3 pi is larger than 2 plus pi, so this is smaller than the boundary point of the domain. So this is actually interior to the domain. Now we want to make sure that this is a maximum area, so for that we can take the second derivative of a, which is just minus 4 plus 3 pi over 4. That's less than 0, indicating that the graph is concave down, indicating that the critical point must be a maximum. So this is the x value that will maximize the area. So finally, we just have to plug this x value back into the equation for area, and that tells us what the maximum area is. So x star, let's move some space up here. Actually, we don't need any of this anymore. So okay, actually, let's do it like this. Okay, so x star, critical point, is 200 over 4 plus 3 pi. So next we want to insert that into the equation for area to find the maximum possible area. So basically the maximum area is 50 times this. So 50 times 200, so 2,000, 10,000 over 4 plus 3 pi, and then minus 4 plus 3 pi over 8 times 200 squared, so that's 40,000 over 4 plus 3 pi squared. And you'll notice that one factor cancels like this, and then 40,000 over 8 would be 5,000. So 10,000 over 4 plus 3 pi minus 5,000, the maximum area, 10,000 minus 5,000, 5,000 over 4 plus 3 pi. So in whatever units the perimeter are measured in squared, this would be the maximum area for the window.